Hello, this is Mr. Montgomery. In this video, we're going to be looking at 6 example problems dealing with work and power. This video is designed especially for my Physical Science 1 lab students that are taking lab online to help you with the calculations you're going to be doing in that lab. I'm going to put a link in the description to these example problems and also to that lab that I'm talking about. Okay, so this first work and power example, we want to convert 120 pounds to newtons. Pounds is the English system unit for force. Newtons is a metric system unit for force. So it tells us right here 1 pound is 4.45 newtons. So if we have 120 pounds, then we want those pounds to cancel out. We want to end up with newtons. So we're going to plug in our conversion factor. This 1 pound is 4.45 newtons. And so pounds divided by pounds is going to cancel. I'm going to do 120 times 4.45. And that is going to give me 534 newtons. Okay. All right, number 2. Says a 500 Newton person, so it's telling the weight of this person, climbs 3.5 meter tall flight of stairs. How much work is done? Okay, well, work is equivalent to force times distance. And so the force here is the weight of this person, 500 newtons. And they climb a distance of 3.5 meters going up the stairs. And so this work, 500 times 3.5, I have 1,750 joules. A joule is a newton times a meter. It's a standard unit for work in the metric system. Number 3. Says a person does 2,500 joules of work in 8.5 seconds. How much power does the person exert? Measured in watts and also measured in horsepower. All right, so power is equivalent to work divided by time. So if I want to take those 2,500 joules of work divided by 8.5 seconds of time. So 2,500 divided by 8.5. Then my power is 294 watts. Okay, a joule divided by a second is a watt. Second part of this question says, what is that equal to in horsepower? So right here, 1 horsepower is equivalent to 746 watts. So if I take my 294 watts and I want to convert this, horsepower on top, so I can convert to horsepower, but one of those is 746 watts. The watts are going to cancel out. I have 294 divided by 746. And I get 0.39 horsepower. 0.39 horsepower. Okay. Question number 4 says a person needs to perform 3,200 joules of work. If the person's average power is 1 horsepower, how much time is this going to require? All right, so we're told here the work and the power, we're trying to solve for time. Okay, so if power is work divided by time, then I'm going to multiply both sides of this equation by time. I'm going to divide everything by the power. So just rearranging my formula tells me that time is the work divided by the power. All right, so we have 3,200 joules of work to do, but 1 horsepower. Going back to that previous example, 1 horsepower is 746 watts. And so 3,200 divided by 746 is 4.29 seconds. This had to be measured in watts because a watt is really right here a joule per second. That lets my joules cancel out and tells me how many seconds it's going to require to do this work. All right, number 5. A person does 1,800 joules of work. How many calories is that? Calorie is another unit of energy, the same way joule is. And so these 1,800 joules, we're converting those to calories. Well, right here, 1 calorie is equivalent to 4,186 joules. And so joules, we're going to divide, and those are going to cancel out. 1,800 divided by 4,186 tells me that this is equal to 0.43 calories. Important to notice right here, this calorie has a capital C. All right, and then one more. Number 6. A person riding a bicycle burns 25 calories while assuming he's 100% efficient. Comes to find out, he learns that he's really about 25% efficient when his body is converting the energy from the food he's eaten into the motion of his bicycle. So how does this affect the number of calories that are being burned? A lot of times students are going to look at a problem like this and say, well, if you're only 25% efficient, you only burn 25% of these original calories. But if you're less efficient, that means you're wasting energy. You get hot and sweaty pedaling a bicycle. That wasted energy is not helping you move forward, but it's energy that you are burning. So here, really, what's going on, if you're 25% efficient instead of 100% efficient, that means you are 4 times less efficient, and you're going to need 4 times more energy. Less efficient, you need more energy. So in this case, you would actually burn 100 calories on this bike ride, not just 25. So I hope those example problems give you a good idea of the calculations and the problem types that you're going to be solving and working out after you perform your experiment or as you perform your experiment. And as always, if you need more help, then feel free to reach out to me, and y'all have a great day.